Now let us discuss the architecture of TPUs version 1. So just to motivate why we are studying TPUs. So you must have heard of AlphaGo, which is the famous computer program that played against Lee Sedol, the board game Go. It consumes huge energy when it was run on GPU, but when they moved it to TPU, the power consumption reduced drastically. So there are 4 versions of TPU. TPU version 1 is only for inference. Version 2 and 3 are for inference and training, and version 4 is for inference. So in today's talk, I will discuss version 1, 2, and 3. I will not explain version 4. Hopefully, by understanding this, you can easily read their STAR 2021 paper and understand V4. So this first presentation is on version 1. So I'm sure now every computer architect will know about it. So there is a hardware. Now we have some general purpose hardware such as CPU and GPU. And then we have specialized hardware, FPGA and ASIC. CPU is latency oriented, GPU is throughput oriented, FPGA is just a programmable logic, ASIC is fixed logic. Of these, TPU is an ASIC. So that is one reason why it is more efficient than GPU, because GPUs were designed for mostly graphics applications, and later they have been kind of reused for deep learning. But TPU is designed from bottom up for deep learning. So TPU connects to CPU over a PCI Express bus, similar to how GPU connects. So this is the TPU PCB, version 1 PCB. This is the block diagram of TPU. So the key computation workhorse is here. This is the matrix multiply unit. Now here, if you remember, we need to do systolic data setup. So that is done here. Okay. Now the weights are stored in the off-chip memory. They are fetched with the weight fetcher, weight FIFO. Okay. I will describe these one by one. So here, this is the host interface from which it connects to the host. TPU uses a weight stationary architecture. I have already discussed this. Weights are preloaded into the MAC array. And activations come from the left. This is the activation storage buffer. So activation, what is activation? Activation is, so just consider one layer. In one layer, we have inputs and we have weights. So inputs are multiplied with the weights and we get the output. So input, we call it input activation, and the output, we call it output activation. And the activation, we also call it feature map. So sometimes you will hear the word input feature map and output feature map. Sometimes you hear the word input activation and output activation. So the input goes here, weights come here, we get the output, which we accumulate. Then if there are layers such as ReLU or pooling, we apply those here. Then the output comes, we again store it back here. And as you know, in CNNs, the output of one layer becomes the input for the next layer. So this output becomes the input for the next layer. So in this way, we keep on circling. So now, because weights are already preloaded, so that's why weights are read much less frequently than the activations. So bandwidth of activation storage buffer is much higher than that of weight buffer. Okay. Matrix multiply unit. So let us now focus on this matrix multiply unit. So here we have, in the previous example, we had 3x3 systolic array. Here we have 256x256 systolic array. Now there we use the word P or processing unit. Here we are using the word MAC. Both are same. It can perform 8-bit MAC operation on signed or unsigned integers. It supports dense matrix multiplication. If you do sparse matrix multiplication, it is not additionally efficient compared to what a dense matrix multiplication is. It supports systolic execution to save energy by reducing reads and writes. So systolic array we have already explained. So now we can understand. Systolic arrays are heavily pipelined. And to get high performance, the user must keep the matrix multiply unit busy. So because see, in CPUs, you have many techniques for hiding the latency, such as caches, and GPUs have massive multi-threading. Here we don't have all them. So if you don't keep your compute unit busy, your performance is going to be very poor. Okay, we have to keep the compute unit busy to get good performance. So this is the systolic data flow of matrix multiply unit. So here we have this activation memory. Activations come to the left, partial sums keep on moving down. In weights are already stored here. And within a MAC here, we have 8-bit activation, 8-bit weights. The output is 16-bit. We add 24-bit partial sum from the previous step, and that comes here. So let us now focus on accumulator. This is the accumulator and the weight FIFO. So 16-bit products are collected in 4 megabyte of 32-bit accumulators. Weights for the matrix unit are staged through a on-chip weight FIFO. Here, for this weight FIFO, we read the weights from an off-chip 8 gigabyte DDR3 DRAM. Now let us see the unified buffer, which is also called local activation storage. So intermediate results, that means the output of intermediate layers, they are stored in this 24 megabyte on-chip unified buffer. This serves the input to the matrix multiply unit. So to summarize, we have this red loop. So the data, initially the weights are here, then it moves here into accumulator. This activation pipeline is this. This is called activation pipeline. So from this pipeline, then through this activation storage, it keeps on moving data and computation path till we complete all the layers. So computation is done one layer at a time, and then we move to the next layer. So I'm sure you know all about RISC and CISC. RISC has simple instructions, CISC has more complex instruction. Example of RISC is ARM, whereas example of CISC is x86. So what do you think? Which ISA would TPU use? Should it use RISC or should it use CISC? Which ISA would it be using? Any guess? Just make a guess.
CISC.
CISC. Why CISC? Now, why CISC, Tarun?
Because in CISC we can have variable instruction lengths.
So how does it help?
I mean, if there are, for example, if we have data length, if we have different data length, then we can, have different instruction types. That's what I was thinking.
Okay, so Anmol says RISC. Why, Anmol? Why RISC? Why you want to take the risk of saying the answer is RISC? Wait. Let us ask Anmol first, then Naman can reply.
Sir, may I?
Okay, Naman, if Anmol is not speaking, you can go ahead and speak. Yeah.
So, sir, because systolic array is highly pipelined and RISC has a small instruction, so we can put many instructions on these pipelines. So that's why it will get. That's why RISC.
Okay, Surya Prasad says varying instruction length will become a problem. Yes, RISC to have less complexity. Okay, remember here we are not talking about, this is not a general purpose CPU which needs to have so many instructions. So, okay, let us draw the curtain. Unexpected lead follows the CISC ISA. Why? The reason is that since the instructions are sent over the relatively slow PCI Express bus, we send it from the host. So we don't want this. See, what happens is this PCI Express is always the bottleneck. You take any accelerator, whether it be GPU, FPGA. Okay, if you, sorry, actually I have to take an important call. Sorry, this is important. Okay, sorry for the disruption. So there are always this RISC versus CISC battle will never end. Everybody knows about it. However, see, any accelerator you take, GPU, FPGA, we want to Can you see my slide? Can you see my slide?
Yes, sir.
Okay, so any accelerator you take, all this PCI Express becomes a bottleneck. Even here you can see the TPU can chunk out the results very, very fast, but if you have to all the time talk to the host, that becomes a bottleneck. In fact, if you see Microsoft's brain game, there they say that FPGA works so fast that CPU cannot catch up, so they have to keep 2 CPUs with each FPGA. So here also, one of the goals is we want to minimize the communication or the talking with the host, so we want to keep that minimum. And another thing is it's not a general purpose architecture. This is an accelerator. It has just half a dozen instructions. Here we have mentioned 5. Somewhere I read it is 5 to 6 instructions, half a dozen, maybe 6. So you just need to do very simple tasks. You don't need so many instructions. So read host memory, read weights, do matrix multiply, activate, write host memory. And TPU can directly run TensorFlow programs. And because it is CISC, each instruction takes more time, 10 to 20 cycles. But anyway, it's not a latency machine, right? We have this. I hope you know what is the meaning of latency optimized versus throughput optimized. We have already discussed this. For example, here, CPU seeks to minimize latency for each task, and GPU maximizes throughput. So GPU is more about improving the throughput. Here, TPU, especially TPU version 1, this is all about boosting the throughput. Now, one more thing is that TPU version 2, 3, and 4, they use what you call VLIW. I'm sure you have studied about VLIW in another lecture, probably Dr. Biswa or someone who's taught. So there, what happens? TPU itself fetches the instruction from the host. Here, host is sending the instruction, but in TPU version 2, 3, 4, TPU itself fetches the instruction. So there's slight differences, but the ISA still remains CISC. Again, there is always a battle. You can always say, okay, they could have used RISC. Probably they could have, but you don't get much by minimizing the latency. If you, for example, here bring this 10 to 20 cycles, from 10, probably bring it to 2 or 3. You don't need to do any individual additions. Host needs to just say matrix multiply. Host does not need to say do add or subtract. Host is not giving low-level instructions. Host is giving big-level instruction, and then TPU does the whole thing. You're not doing that minor optimization. So that's why the scope is different. Our constraints or parameters are different. So due to simplicity of systolic array, TPU spends only 2% of the overall chip space for the control logic. This is a major improvement. Control is very small. Whereas if you see CPU, they have what branch predictor, out of order, and out of order is a huge saga. Actually, it never ends. Rename buffer, this, that. So, but TPU, because it is accelerator, control logic is kept very, very small. So if you are interested, you can read this. So this was